everyone, and welcome. Today, we are going to take a deep dive into one of the most powerful, and I mean truly versatile components in all of electronics. It's this tiny little chip that is, no joke, the Swiss Army knife for circuits. And trust me, by the end of this, you'll see exactly why. So let's jump right in. All right, let me start by asking you a question. If you could only have one tool, just one single building block, to do pretty much anything you wanted with an analog signal, what would you pick? Well, the answer is this little powerhouse right here, the operational amplifier, or as everyone calls it, the op-amp. At its core, it's a high-gain amplifier, but it's so much more than that. It is the absolute foundation for countless analog circuits. You could say it's the hero of our story today. Now, to really get a grip on what makes the op-amp so special, we first have to look at it in its perfect, idealized form. Just think of this as the theoretical blueprint, It's what every real-world op-amp is trying to be. Okay, so look at these ideal characteristics. They're kind of crazy, right? Infinite input impedance. That means it can read a voltage without drawing any power at all, like a perfect spy just looking at the circuit. And zero output impedance? That means it can drive any load you throw at it perfectly. And then there's infinite gain, a basically limitless power to amplify. Now, of course, no real op-amp is actually perfect, but this ideal model is absolutely key to understanding what it's built to do. So this is where it gets really interesting. You have to think of an op-amp as having two completely different personalities. First, you've got the linear mode, the rule follower. This is when it faithfully preserves and processes a signal. But then, you've got the nonlinear mode, the rule breaker. This is when it totally transforms the signal to make a decision or even create something brand new. First up, let's talk about the op-amp when it's being a total rule follower. In these linear applications, the whole game is about processing a signal, making it bigger, smaller, or maybe combining it with other signals, all while keeping its original shape intact. And the most classic, the absolute textbook example of this is the inverting amplifier. The easiest way to think about this is like a super precise volume knob that also happens to flip the signal upside down. And this is just, it's so elegant. Remember that crazy infinite gain we just talked about? How in the world do you control something like that? Well, it turns out all you need are two simple resistors. The ratio between the feedback resistor, RF, and the input resistor, RIN, lets you dial in the exact amount of amplification you need. It's predictable, it's stable, and it's incredibly powerful. Okay, so that's how you handle one signal. But what if you want to mix a few signals together? Well, for that, we have the summing amplifier. What you're looking at here is basically a tiny, tiny analog computer. No, really. It is literally performing mathematical addition. It takes several different input voltages, combines them, and gives you a single output that is the sum of the inputs. This is the core idea behind every audio mixer ever made, where you're blending the signals from guitars, drums, and vocals all into one track. All right, so we've seen the op-amp when it's being all polite and predictable. Now, let's check out its wild side, the rule breaker. This is where we stop trying to preserve the signal and instead use the op-amp's raw, untamed power to make some serious decisions. And the number one job for the rule-breaking op-amp? Being a comparator. This is the op-amp in its purest, most fundamental decision-making mode.
See, in this mode, it's not about amplifying anymore. It's about deciding. All a comparator does is ask one simple question. Is this voltage higher than that other voltage? That's it. And based on the answer, its output just slams all the way to the maximum positive voltage or all the way to the minimum. It's a binary yes or no answer. This one simple decision is the crucial bridge from the analog world to the digital world.
But the op-amp's rule breaking doesn't stop at just making decisions. What happens if you don't even have a signal to begin with? Well, the op-amp's got you covered there too. It can go from being a processor to being a creator. Yeah, with some clever feedback circuits, you can get op-amps to oscillate, basically creating brand new signals right out of thin air. We're talking about those crisp on-off digital clocks of a square wave, the smooth ramp of a triangular wave, or even the pure tone of a sine wave. These are the fundamental waveforms for everything from synthesizers to timers. Okay, enough theory. We've seen the rule follower and the rule breaker. Let's make this totally concrete and walk through how we'd solve a practical, real-world problem. So imagine you're building a project. You've got a sensor, maybe it measures temperature, maybe light, who knows? And the signal it puts out is tiny, just zero point 0.2 volts. That is way, way too weak for a computer or a microcontroller to read reliably. We need to get that signal up to a nice strong 5 volts. So, how do we do it? So what's our game plan? Well, it's actually super straightforward. Step 1. What's the goal? We need to turn 0.2 volts into 5 volts. Simple enough. Step 2. Let's calculate the gain we need. Just divide 5 by 0.2, and we get 25. So we need a gain of 25. Step 3. Pick our circuit. The inverting amplifier is perfect for this. All we need to do is pick 2 resistors whose ratio is 25. So let's say we pick a 10K ohm resistor for the input. That means our feedback resistor needs to be 250K ohms. And step 4, problem solved. Just like that, our tiny, useless signal is now a strong, clean signal a computer can easily understand. And that's really the magic of it all. It comes down to this one component. Think about everything we just saw. A precision amplifier, a little calculator, a decision maker, even a signal creator. All of that functionality packed into one single chip. So you see, whether it's carefully following the rules to faithfully amplify a signal, or just throwing those rules out the window to make a decision, the op-amp and its 2 personalities are absolutely at the heart of modern analog design. And the crazy part is, these things are everywhere. I mean, literally everywhere. They're working silently in your headphones, in your car's stereo, in life-saving medical equipment. They are the invisible workhorses that make so much of our electronic world tick. So the real question is, now that you know what they do, where are you going to spot their handiwork next?